Hello everyone. In this video lecture, we are going to discuss about the chemistry of main group elements, and this topic is included into the BSc 5th semester of the third year student of Guru Jambeswar University of Science and Technology, Hisar, and I am Dr. Kuldeep. So let's start. And this lecture is lecture number 4 in this lecture series. In the unit number 1, we have already discussed the topic like diborane and the concept of multicenter bonding and the structure, bonding and properties of the hydrides of group 13 and group 14 elements in the previous 3 lectures. So in this lecture, we are going to discuss about the hydrides of the group 15 elements. So let's start. The hydride of group 15 elements. First of all, the group 15 consists of the following elements: the nitrogen, which is a non-metal; phosphorus, again a non-metal; arsenic and antimony are the metalloids; and bismuth is a typical metal. So these 5 elements we are going to discuss in the group 15 element, the hydrides of these 5 elements. If we talk about the trihydrides of the formula EH3, general formula EH3, the element E is nitrogen, phosphorus, arsenic, antimony and the bismuth, the EH3 type hydrides. If we discuss about the boiling point, the trend in the boiling point, the hydride of nitrogen, trihydride of nitrogen, which is popular name ammonia, has a boiling point higher than PH3, phosphine, and then the phosphine has lesser boiling point than arsine, and then stibine, and then bismuthine. So there is no regular trend in the boiling point of the hydride of the trihydride of the group 15 elements. The ammonia has larger boiling point than phosphine is due to the strong hydrogen bonding which exists in the ammonia, and the NH3 molecule are associated strongly. So due to strong hydrogen bonding, the ammonia has higher boiling point than the PH3. But as we go from phosphorus to bismuth, the boiling point is again increasing. This attributed to the increase in the size of the central element, which increases the non-covalent interaction. So that's why the boiling point again increases from phosphine to BiS3. The thermal stability, if we talk about the thermal stability of the molecule, the thermal stability decreases as we go from ammonia to BiS3. The BiS3 molecule is not very stable. The stability is up to SbS3. The BiS3 molecule is highly unstable molecule. The thermal stability decreases from ammonia to BiS3. So ammonia is maximum stable among these hydrides. What is the reason behind this? The covalent bond enthalpy. The bond enthalpy, the bond strength of EH bond is like this. The NH bond is the bond energy of bond enthalpy is 391 kilojoule per mole. Down the group it decreases 322 and it is 296. So that's why the thermal stability decreases going from NH3 to PiH3. The basic character. Basic character means the tendency to donate the lone pair of electron present on the central atom E towards a Lewis acid. So the basics or the basic character is decreases. NH3 has a lone pair nitrogen, then phosphorus also lone pair, then arsenic, antimony, bismuth. So the probability of or the tendency to donate these lone pair of electron to some Lewis acid is decreases as we go from NH3 to BiH3. This is the trend in the basic character. So the lone pair are mostly available on the nitrogen in case of ammonia, and it is least available on bismuth in case of BiS3. The reducing character is following the reverse order as the basic character. As we know, the EH bond strength is decreases from ammonia to BiS3. That's why the BiS3 is the strongest reducing agent and the ammonia is the least strong reducing agent. Then synthesis part, how can we synthesize the hydride of 15 group element? For the synthesis of ammonia, we can use lithium nitride and hydrolysis with the water molecule produces the ammonia. Another method is by using the ammonium chloride and the calcium hydroxide. The ammonia is produced. Or we can reduce the zinc, any nitrate salt with zinc in the basic medium and we will get the ammonia. Another method or a general method for the preparation of hydride, we can take the ECl3 type salt like PCl3, ASCl3 and reduce with the lithium aluminum hydride in diethyl ether. We will get the EH3 where E is phosphorus, arsenic, antimony and bismuth. We can similarly use calcium phosphide Ca3P2 hydrolyze with water and we will get the phosphine. And the another we can use the iodide salt with potassium hydroxide and we also get the phosphine. The commercial synthesis of phosphine uses the disproportionation of white phosphorus in the basic solution. Disproportionation means the same molecule is oxidized and reduced. So phosphorus, elemental phosphorus, when treated with water in the basic medium, we get the phosphine gas and the H2PO2 minus in the aqueous solution. The industrial manufacturing of ammonia, which is very important, involves the Haber process. Haber process is a well-known process which is used for the production of ammonia, and ammonia is a very useful compound which is further used for the manufacturing of fertilizers. The 1 mole of nitrogen when treated with the 3 mole of hydrogen, we get the 2 mole of ammonia. This is a reversible reaction and the delta H is negative, the reaction is exothermic, and delta G is also negative when the reaction is feasible. But the decrease in the number of moles of gas means that entropy is negative, which is a problem. So the number of mole in the reactant are 3 plus 1 4 and the number of mole in the product are 2. So the entropy change is 2 minus 4 minus 2 which is negative. So for the industrial sustainability, for the industrial purpose, the ammonia must be formed in optimum yield and at a reasonable rate. So for the industrial purpose, we require both things. First, the rate should be fast and the yield should be high. But as we know, this is an exothermic reaction. If you increase the temperature, then rate of reaction decreases. Then increasing the temperature increases the rate of reaction. When you increase the temperature, it increases the rate of reaction but decreases the yield since the forward reaction is exothermic. So for at a given temperature, both the equilibrium yield and reaction rate are increased by working at high pressure. So the optimum condition are the temperature 723 Kelvin, pressure 20,260 kilopascal, and we use the catalyst iron 3 oxide Fe3O4 mixed with potassium oxide, silica and aluminium oxide as the heterogeneous catalyst. So industrially, the ammonia is produced by the nitrogen and hydrogen in the presence of the catalyst at this temperature and this much pressure. Then come to the structure and the bonding part, ammonia is a colorless gas with a pungent odor. Shape of the molecule is pyramidal, which can be explained by considering the sp3 hybridization of the nitrogen. As we know, the nitrogen has the electronic configuration, the valence shell electronic configuration is 2s2 and 2px1, 2py1 and 2pz1. So in the valence shell, there are 5 electrons on the nitrogen atom. If we consider the sp3 hybridization, if we consider there is 1 electron and there are 2 electrons, so sp3, so there are 4 sp3. So these 2 electrons will remain in either of the orbital, either in 2pz or in 2py or 2px or 2s. So upon hybridization, we are getting 4 sp3 hybrid orbital, out of which 3 are singly occupied and 1 is doubly occupied. And this lone pair is present in one of the sp3 orbital, and these 3 single electron will form the bond with the hydrogen atom, the 1s orbital of the hydrogen atom, and this is a pyramidal shape like this. This is a formation of triangle, and at the center of triangle, above the plane of the triangle, there is nitrogen, and so the shape of the ammonia is pyramidal. And ammonia is a water-soluble weak base. The acidity or basicity can be measured by the pK and pKb values. When ammonia is dissolved in water, liquid water, we will get the ammonium ion and the hydroxide ion, and these hydroxide ion is the cause of the basicity of the ammonia. And the pKb value is 4.75, which indicates the ammonia is a weak base in the water. And all the group 15 hydrides are pyramidal like ammonia, but the bond angle decreases down the group. So the maximum bond angle is observed in ammonia NH3, and the least bond angle is observed in the BiH3. Why this trend? So in ammonia, the angle is around 108 degree, but as we are going down the SbH3, the angle is 91.3 degree. We are not considering the BiH3 here because the BiH3 molecule is highly unstable molecule, so not much data is available for BiH3. So we are talking about the 4 molecule only: NH3, PH3, ASH3 and SbH3. So the bond angle is decreases down the. So if we draw the structure like this, E molecule is pyramidal, H where E is either nitrogen or phosphorus or arsenic or antimony. This is a lone pair. So this angle is suppose theta, and this angle is decreases from approximately 108 degree to 91.3 degree. What is the reason behind this? The bond pair in the EH bond are responsible for this trend. As in case of ammonia, the size of nitrogen is small, so these bond pair are very close to each other, and that's why they are repelling to each other. So we are getting the maximum value of bond angle in case of ammonia. But as we go to the SbH3, the size of the central atom is increases, and the repulsion between the EH bond pair is decreases, and we are getting the smaller bond angle in case of SbH3. So the large change in the bond angle has been attributed to a decrease in the extent of sp3 hybridization from ammonia to SbH3, but is more likely to be due to the steric effects. the EH bonding pair of electrons will repel each other. This repulsion is greatest when the central atom E is small, that is ammonia, and the hydrogen atom will be as far away from each other as possible in near tetrahedral arrangement. As the size of the central atom is increased down the series, the repulsion between bonding pair decreases and the bond angle is close to 90 degrees. So, the repulsion is the main cause for this trend in the bond angle. So, when the EH bonding pair of electron will repel each other. So, when the size is small, the size of E is small, there is maximum repulsion between the bonding pair and we are getting the maximum angle. But as we are going down the group, the size of the central atom E increases and this repulsion is also increases, and that's why repulsion is decreasing and the bond angle is decreases. Then come to the next hydrides of the elements, the hydrazine and the hydroxyl amine. The hydrazine with formula N2H4 or NH2NH2 is a fuming colorless liquid with an odor like that of ammonia. It has a liquid range similar to that of water from 2 to 114 degrees centigrade, indicating the presence of hydrogen bonding. In the liquid phase, hydrazine adopts a gauge conformation around the nitrogen-nitrogen bond like this. This is blue color is nitrogen and the white color are the hydrogen. So the angle is 95 degree and this angle HNH is 108 degree and the nitrogen-nitrogen bond length is 145 picometer. How we will synthesize the hydrogen? This process is known as pressing process. Aqueous ammonia is treated with sodium hypochlorite and we get NH2Cl and sodium hydroxide, and in the next reaction ammonia reacts with NH2Cl and we will get the N2H4 in the aqueous solution. And hydrogen is weaker base even than the ammonia. When dissolved in water we will get the hydroxide ion. So pKb1 is 7.93. The ammonia has pKb of 4.75. It is even weaker than the ammonia, and the pKb2 value is even less, even more. So the overall the hydrogen is a weaker base than the ammonia. The major use of hydrazine and its methyl derivative like CH3NH2 and CH3 twice NH2 is as a rocket fuel. Hydrazine is also used as a foam blowing agent and as a treatment in boiler water to spence dissolved oxygen and prevent oxidation of the pipes. Both hydrazine and N2H5 plus are reducing agent and are used in the recovery of the precious metals. And next hydride is hydrazoic acid or known as hydrogen azide. HN3 is acidic in the nature. It behaves both as an oxidizing as well as reducing agent. The azide ion has 16 electrons and is isoelectronic with carbon dioxide. The structure of the azide ion is very similar to the CO2. It is a linear molecule. This is hydrozoic acid. The N and distances are different. It is 1.13 and 1.24, and this is the resonance, one of the resonance structures of the hydrozoic acid. Hydrozoic acid or hydrogen azide as we are continuing. So this is the structure. The blue ball are nitrogen and the white ball is the hydrogen. Here the bond length or bond angle are shown here. The angle is 114 degree and the NH bond distance is 102 picometer, and this is the structure of the hydrozoic acid, three-dimensional structure. And if we are going to the resonance form of the molecule, then this is the one of the resonance form. So this is one and this is If we move these electron pair here and these electron pair here, and we will get the second resonance structure. And this is the structure of the azide ion. The structure of the azide ion, the ion is symmetrical but bond distances vary slightly in different salts. And this is the principal resonance structure of the azide ion. Then hydrazine and hydroxylamine. The again next molecule is hydroxylamine. We have already discussed about the hydrazine. The next molecule is hydroxylamine with the formula NH2OH. And this is the three-dimensional structure of the hydroxylamine molecule. The blue color is nitrogen, the red is oxygen, and the other white colored balls are representing the hydrogen atoms. Hydroxylamine is a colorless hygroscopic solid with a low melting point. It is usually available as a hydrochloride salt or in the aqueous solution. It is a weaker base than either ammonia or the hydrazine. So it is weaker than both of the molecule like ammonia and the hydrazine, as we have discussed earlier. When it is dissolved in water, the pKb value is 8.18, which indicates it is even weaker base than ammonia and the hydrazine. The anhydrous hydroxylamine can also be prepared by adding the sodium hydroxide. This is sodium hydroxide into the aqueous solution of the hydroxylamine, the chloride salt, and we will get the NH2OH in the solution, and NaCl and is separated out, filtered off, and the hydroxylamine precipitated by addition of the ether, that is diethyl ether. The major commercial use of the hydroxylamine is in the synthesis of caprolactam, which is an intermediate in the manufacturing of nylon. Then come to the other member of the hydrides of the other member of the group 15, that is phosphorus, arsenic, and antimony. The molecule corresponding hydride are phosphine, arsine, and stibine. Unlike liquid ammonia, liquid phosphine, arsine, and stibine do not associate through hydrogen bonding. Their much more stable alkyl and aryl analogues are useful as soft ligands. Soft ligands are those ligands which have the donor atom like phosphorus, sulfur, and arsen. In contrast to the commanding role that ammonia plays in nitrogen chemistry, the highly poisonous hydrides of the heavier non-metallic element of group 15, particularly phosphine and arsine, are of minor importance in the chemistry of their respective elements. But both phosphine and arsine are used in the semiconductor industry to dope silicon or to prepare other semiconductor compounds. Phosphine and arsine are poisonous gases and that readily ignites in air, but the much more stable organic derivative PR and ASR3, if you replace the hydrogen atom with the alkyl or the aryl group, then these are widely used as the ligand in the metal coordination chemistry. So the phosphine and arsine, which are highly poisonous, can be converted to useful ligand by replacing the hydrogen by the alkyl or the aryl. In contrast with the hard donor properties of ammonia, as we know that ammonia is a hard ligand because the donor element is nitrogen in ammonia, which is considered as a hard ligand according to the HSAB principle. And alkylamine ligand, the organophosphines and organoarsine such as P(C2H5) thrice and arsenic C6 thrice are soft ligands and are therefore often incorporated into the metal complexes having central metal atom in low oxidation state. So the metal in the low oxidation state and the metal from the 4D and 5D series are soft in nature, and the phosphorus and the arsenic donor ligand are also soap combined with each other, and we are getting the stable complexes. So these are the trialkyl or trialyl phosphine and arsen are used as a soft ligand to bind with the metal in the low oxidation states. The stability of these complexes correlates with the soft acceptor nature of the metal in low oxidation state and the stability of soft donor soft acceptor combination. Thanks for watching the video.